Welcome everyone to the sixth session of the St. Paul's Ministry of Defense. We are right in the middle of our 5-part series on the existence of God, because in defending the Catholic Christian framework, it all starts with God. If God doesn't exist, then none of the rest of the stuff matters. Jesus' revelation, the Catholic Church, none of it matters if you don't have God at the center of reality. And so we've already looked at two arguments for God's existence, the argument from contingency and the moral argument. Today we're going to be looking at our third and final argument of the series, the argument from design, which, as you'll see, is sort of a combination of two different arguments that have lumped together to form one grand argument from design, I call it. Now, with the contingency argument and with cosmological arguments in general, they analyze the universe, or the realm of non-fundamental things or contingent things, and they reason that because the universe, because it has some feature to it, therefore it isn't self-explanatory. It requires some cause to explain its existence, either the fact that it has a beginning, or that it's contingent, right, that it could have failed to exist, or anything like that. So it reasons from creation to a creator, and then does a conceptual analysis of what sort of attributes that cause of the universe, or that cause of non-fundamental things we need to have, and then arrives at a being that everybody understands to be God, as Aquinas is so famous for saying. The moral argument saw that in order to ground objective moral values and duties, you need a perfect divine nature and a divine lawgiver to institute obligations. So we've seen so far that God is both the best explanation for why anything exists at all rather than nothing, and that God is the best explanation of the objectivity of moral values and duties. And today, we're going to be arguing that God is the best explanation for the apparent design of the universe. So let's get into the argument from design. I've broken it down into two premises and then a conclusion. Premise 1. If the universe exhibits features that are best explained by design, then there is a transcendent designer of the universe. So you'll notice this is an inference to the best explanation argument. It's not a proof. It's just saying that one explanation is going to be the best of all the plausible candidates to explain the data in front of us. So it's an inference to the best explanation, it's called. Premise 2. The universe, with its initial cosmic constants and quantities fine-tuned for the possibility of the existence of intelligent life, and its elegant mathematical applicability, exhibits features that are best explained by design. Therefore, there is a transcendent designer of the universe. So as cosmological arguments moved from creation to creator, this design argument and design arguments in general move from design to designer. So let's now examine both of those features of design in turn. We'll begin with the fine-tuning of the universe. So there's an observation, right, that's been taking place over the last 50 years. What physicists have been discovering is that when you analyze the universe and its nature, it has the precise structures that it would need to have in order for life to even be possible. People have said that the fundamental structure of the universe is, quote, balanced on a razor's edge for the existence of life. In other words, it has been fine-tuned for the possibility of the existence of life. So what do we actually mean by fine-tuning? Well, there are laws of nature, right? Laws that govern the regularities and govern the order of the universe. There are constants, right? So the physical laws of nature, right, when they're given mathematical expression, contain various constants. For example, the gravitational constant, whose values are not determined by the laws themselves, right? And then you have quantities. So these are quantities of different physical objects and states of affairs at the initial state of the universe. So maybe the amount of heat, or the amount of entropy, or the distribution of the masses of various objects, or something like that, amount of energy. So when we say that there's fine-tuning, we're talking about the constants and quantities and those laws. We're specifically going to focus on the constants and quantities for today. And so when we say fine-tuning, what we're meaning to say is that if you have small deviations from the actual values of those constants and quantities, then the universe would become life prohibiting, it would have originally been, and it would have always been, life prohibiting. In other words, the range of life permitting values is exquisitely narrow in comparison with the range of assumable values. So if you look at all the values that these constants and quantities could have taken on, only a very small portion of them would have rendered the universe life permitting. People have described the universe we live in as a Goldilocks universe. And so now let's get into 3 examples of fine-tuning, although physicists argue that there are more than 20 of such examples. Sometimes there are over 30 examples, depending on who you listen to. So example number 1, the cosmological constant. So the cosmological constant is a term in Einstein's equation of general relativity that, when positive, acts as a repulsive force, causing space to expand, and when negative, acts as an attractive force, causing space to contract. So the cosmological constant is a constant in the equation that dictates the rate of expansion of the universe. And physicists have calculated that the cosmological constant is fine-tuned to 1 part in 10 to the 120th. So if the cosmological constant was different by 1 part in 10 to the 120th, the universe would have been life permitting. There would be no human beings around today. There would be no life at all today. Sticking with this theme of the rate of expansion of the universe, we have the strength of gravity next. So gravity is the weakest of all the forces, to give a little bit of background, although it's still incredibly strong, but the other forces are much, much stronger than gravity. Now, looking at that equation and all the different factors that influence the rate of expansion, if you hold all of those other factors besides gravity constant, and you just look at the strength of gravity, if it were larger or smaller by an estimated 1 part in 10 to the 60th of its current value, then the universe would have either expanded too quickly for galaxies or stars to form, or collapsed back on itself too quickly for life to evolve. Either way, you don't have life if it was different by any amount. By an amount even that small. So the third example would be the mass of neutrons. So neutrons are just a tad heavier than protons. And if this were the other way around, then atoms could not exist, because all the protons in the universe would have decayed into neutrons shortly after the Big Bang. Now, if you have no protons, then you have no atomic nucleuses, and thus no atoms. But if you have no atoms, you have no chemistry. If you have no chemistry, then you have no life. So it seems that also the mass of neutrons is fine-tuned for the possibility of the existence of life. And it's fine-tuned to such a precise degree as well. It needed to be exactly 1.001 times the mass of protons, referring to neutrons. If we're off by even just a bit, there'd be no life in the universe. Now, the most common objection that you'll hear to this idea that the universe is fine-tuned for the existence of life will be from the layman, right? You won't hear this from the scientist or the philosopher, but you will hear it from the average person on the street that you're sharing this with, if he's read to some extent, or if he's even heard of this. Or most likely he's heard of it from somewhere on the internet and hasn't actually looked at the science or thought deeply about it. But the objection is they'll tell you, okay, yeah, maybe if the universe had different initial constants and quantities, then yeah, we wouldn't have seen life as we know it today. But you can't move from the fact that we wouldn't see life as we know it today to saying we wouldn't see life at all, right? Maybe different forms of life could have evolved, right? So maybe we wouldn't have carbon-based life, but maybe you could have something else, like a nitrate-based life or something. Now, the problem with this is that when we say that life could not have existed, that the universe would have been life prohibiting if these values are different, we're not talking about any specific type of life, right? We're not getting fancy here. We're being very minimal. We're defining life as any stable, reproducible mechanism. So by life, scientists just mean that property of organisms, right, that to take in food, extracts energy, that grows, adapts to environment, and reproduces. So you wouldn't have anything like that if these values were different. No life at all would have been able to develop, if not for a universe with values in the narrow life-permitting range. Because think about it, if you have no planets, if you have no chemistry, there's no way you can even have the ingredients for life. So it's not about any particular type of life, it's about any stable reproducing mechanism. So be sure to explain that, because I think fundamentally it's just a misconception, and it isn't something you hear from the experts. As a great physicist Stephen Hawking said, the remarkable fact is that the values of the physical constants appear to have been finely tuned to enable the development of life. So given that the universe is fine-tuned, and we just saw 3 examples, there are dozens of examples, the next natural question is to ask what the explanation is for that fine-tuning. It appears that there's 3 options on the table. The explanation of the fine-tuning of the initial cosmic constants and quantities of the universe is either physical necessity, chance, or design. So let's evaluate each of these possible explanations in turn. Physical necessity. So this hypothesis states that the constants and quantities have the values they do out of necessity. There was thus no chance of the universe being life-prohibiting, because the values fall within the life-permitting range, but really there is no range that extends beyond that life-permitting one. Or, more narrowly than that, there is no range at all. The values that we've currently observed exhaust the totality of the range. These values are the only values that those constants and quantities could have ever taken. So it's necessary that the universe is fine-tuned for life. It's physically necessary. There's something about the universe that makes it required that it has those particular values. Now, this is a hypothesis that is extraordinarily implausible, right? Physicists calculate that there's actually a wide range of seemingly possible alternative values that these constants and quantities could have taken on. That's where we get numbers like 10 to the 120th or 10 to the 60th or something like that. So it just doesn't seem to be true at all that there's a physical necessity to the constants and quantities having these values, right? And in any case, even if that was the case, right, that there's physical necessity, the burden would be on the person arguing that to sustain evidence to make one believe why we should render them necessary, why we should recognize them as necessary. Because the burden of evidence always lies on the person who isn't arguing for possibility. Possibility in anything seems to be the default option, right? That, oh, things could have been otherwise. That's always the default. If you want to say, no, things had to have this way, then the burden of explanation lies on you. And it doesn't seem that any evidence has been given for that, or even that could be given for that. It just seems remarkably implausible that these values had to be as precise as they were, especially when you look at how many decimal places these numbers take on. The idea that they couldn't have differed even slightly is just unbelievable. It borders on incredulity. Now, this hypothesis of physical necessity is ruled out by the great majority of physicists and philosophers who study this argument, and so really it's no longer a live option on the table. Even the most vociferous atheists, like Richard Dawkins, for instance, who's not an expert in this, but who has studied the argument, has said, yes, atheists should abandon this line of reasoning because it's not salvageable. It just does not appear that these values are physically necessary. So now that we've removed physical necessity, it seems that the only live alternative to design is that of chance. The chance hypothesis is that the universe's constants and quantities have the values they do by random chance. Their taking on these values was not necessary, but it wasn't intentional either. It was just random chance. They could have taken on different values, but they took on these ones, and we're here. Now, there's a misunderstanding that's very pervasive on the popular level, less so amongst the experts, but still there. But this is the idea that it's really not surprising the universe is fine-tuned. And they're going to say, because we're here. That's why it's not surprising. If the universe wasn't fine-tuned, then we wouldn't even be here. So the fact that we're here tells us that the probability that the universe was fine-tuned was 1. It's not 0.0000, right, basically ad infinitum. It's just 1, because if it wasn't, we wouldn't even be here. But since we're here and we wake up, we see the universe, it had to have been fine-tuned. So we shouldn't be surprised at all that it is, right? You'll hear this all the time. The problem is that this is a fundamental misunderstanding of the question we're asking about fine-tuning. This claim here confuses the following 2 propositions. One, they confuse the true claim that if observers who have evolved within a universe observe its constants and quantities, it is highly probable that they will observe them to be fine-tuned for the existence of life. So they confuse that true claim with a false claim that it is highly probable that a universe exists which is finely tuned for the evolution of observers within it. So clearly, right, if we're here and we can even ask the question, have this debate, then that means that the universe was indeed fine-tuned. So yeah, if we're here, we should expect to see a fine-tuned universe, of course. But that's not what we're asking. We're asking for the prior probability of there being a fine-tuned universe, not the posterior probability of human beings already on the scene. That's just fine-tuning, right? That it had to be in that narrow range. So that part's not surprising, that if we're here, the universe should be fine-tuned. We're asking, why is the universe fine-tuned in the first place? Why does the universe even have those conditions and parameters that would allow for intelligent life? It would be like the following demonstration, the following example given by the philosopher John Leslie. So he imagines a situation where you're dragged before a firing squad of 100 trained marksmen to be executed. The command is given, ready, aim, fire, and then you hear the deafening roar of the guns. But after all the shots are taken, you notice that you're still alive. Now, if your friend who was there viewing the spectacle said, "Hey, you're alive, isn't that crazy? Aren't you so surprised?" And then you'd be like, and then he was like, all the shots missed, right? All the shots missed. Aren't you surprised by that? And then what if he said, "Of course I'm not surprised, because I'm here standing to you right now. So that means that they must have missed, because I'm here right now." But yeah, if you're there right now after the shooting, then of course they must have missed. That's not surprising. The surprising thing is, why did they miss in the first place, right? So that's the question we have to ask. Not given that we're here, is it probable that we should observe a fine-tuned world? Of course we should. The question is, why is there a fine-tuned world in the first place? It seems very surprising, especially on the chance hypothesis, because it was just so unlikely. Now, the unlikeliest form of the chance hypothesis is one in which there's only one universe, which is the one we're living in. And so basically, the universe only had one shot of having life-permitting values, and if it just did have those, the probability that would take on each one of those is so low, not to consider the cumulative probability of having all of them be in the life-permitting range. Well, yeah, then that seems, right, infinitesimally small. Then it seems the design hypothesis should, of course, be preferred over this one, right? Even if we don't know the probability of God wanting to create a world that was fine-tuned for life, we can at least say it's not unreasonably low. Whereas with the chance hypothesis, if it only had one shot to have these values, and it had them all in the first, right? When we're talking about numbers like 1 out of 1 to 1 over 10 to the 60th, well then yeah, that seems kind of unbelievable. It seems like we should prefer one to the other. But because of that, the chance hypothesis has been strengthened by an appeal to what's called the multiverse. So the multiverse hypothesis states that physical reality is best understood not as one universe, but as an ensemble or collection of universes, of which our world is just one member of. So our world, our universe, is just one of many. Different models of physics, different theories of physics that posit different models of the multiverse include different kinds of multiverses. So on some models of multiverse, you have a finite number of universes, maybe like 10 to the 40th or something like that, whereas in others you have an infinite collection. So that'll depend on the theory of physics that undergirds that particular hypothesis. Now, the claim here, which seems true, is that if the expanse of the ensemble, right, if the collection has an infinite number of members, right, so if there's an infinite number of universes, then it's unsurprising that some of them would be finely tuned universes, right? Because as small as these values are, they're not zero. So yeah, maybe it's like 10 to the 120th, right? 1 over 10 to the 120th would be life permitting. But if you have an infinite number, then you will have finely tuned universes. And we happen to be existing in one of them because we're here. But since there were so many, it's not improbable that you would see any. So you don't have a low prior probability, and you have a very high posterior probability. So it seems that the multiverse provides a good explanation for the fine-tuning of this universe. It's just one of many. Basically, the multiverse had an infinite number of tries to get something that is improbable. But with an infinite number of tries, it seems like you will get something that is improbable if you only had one shot. So that's basically the multiverse objection, and it is the strongest objection to the fine-tuning argument in the literature today. Nothing else really comes close. So that anthropic principle we talked about in the last slide is paired with this multiverse hypothesis to create a very powerful and very serious objection. So what should the response be to this idea that the multiverse best explains the fine-tuning of our universe for the possibility of intelligent life? Well, I think we can say a couple of things on this in analysis. First, there's currently no independent evidence for a multiverse, and some speculate whether or not there even could be in principle. So, for example, in order for us to even know whether the universe is one member of many, physicists debate like what the criteria would be for knowing that. Some think we would need to actually physically interact with one of the other ones. We need to bump into them. Or maybe a theory of physics would need to be proven that gives you a multiverse. But it's debated whether or not we could even know that we're in one. And certainly as it stands today, there's no independent evidence for a multiverse. Whereas there is independent evidence for a designer and creator of the universe, right, for God, in the form of dozens of other arguments for his existence. So if you're just looking at this on a surface level, it seems that the design hypothesis is to be preferred, since we have independent evidence for one explanation versus a lack of independent evidence for the other. But we can say more. So one, not all multiverse models posit an infinite collection of worlds, as we've seen, right? Some posit a finite collection. Now, if it's finite, then the sting of fine-tuning remains. Because if you have, let's say, 10 to the 40th, right, number of universes, but we see constant quantities that are fine-tuned and that have the likelihood of taking on the values they do, right, to the order of 1 over 10 to the 120th, for instance, well, then even with that large finite collection, you still would be very surprised to find that you have any life-permitting world under those parameters. And so therefore, the sting of fine-tuning is not necessarily removed by positing multiverse, because it could just be a finite collection, not an infinite one. So clearly, the stronger version of the objection here is going to posit an infinite collection. Now here, we can say a couple of things. So some physicists have argued that the multiverse hypothesis would not eliminate fine-tuning, it would just push it to a different level. So for example, inflationary cosmology or string theory might produce many universes with varying constants, but those frameworks depend on precise physical laws and parameters. So you haven't eliminated fine-tuning, you've just moved it up a level from our universe to that multiverse generating mechanism, or to those equations or those initial states that govern the behavior of the multiverse. So the cosmologist Luke Barnes phrases it this way: a multiverse needs a universe-generating machine, and that machine must have the right settings to make life-permitting universes possible at all. So you may not even remove fine-tuning, even with an infinite multiverse. Secondly, features that would accompany an infinite multiverse have not been observed. So Alexander Vilenkin, a world-famous physicist at Tufts University up in Massachusetts, is insistent that we live in a multiverse. But his whole multiverse scenario depends on the hypothesis of future and eternal inflation, which in turn is based on the existence of certain primordial scalar fields which govern inflation. The problem is that these scalar fields, we don't know whether or not they exist in nature. There is no direct evidence for their existence. We've never observed them. And it's a question of whether or not we should be able to, right? If we should expect to be able to observe them, if they did exist. So it doesn't seem very plausible on the surface that these infinite multiverse theories are true, but if they are, they certainly have a lot of work to be done in terms of establishing them, or even getting the possibility, even getting them off the ground. And then there's the inverse gambler's fallacy. So you could never reason to a multiverse, or in any case to a large number of attempts or tries, just on the observation of one improbable outcome. So for example, if you walked into a casino and the first roll you see lands on double sixes, that doesn't necessarily mean that that person rolled the dice dozens of times before that to get to double sixes, just because double sixes is an improbable outcome. you could still get improbable things on the first try. So you couldn't reason that there had to be a number of tries in order to get there. So that's the inverse gambler's fallacy. So in no way can we say that just on the basis of it being rare that the universe had this, or improbable the universe had these values, that therefore there was a whole bunch of tries to get there first in the form of an infinite number of other universes. So while the multiverse hypothesis is strong and is serious, there are reasons to be skeptical at the end of the day whether or not it really is the best explanation of the fine-tuning of the universe. So we've seen that there are three possible explanations of fine-tuning, and additionally, that two of them don't work. Neither physical necessity nor chance seems to adequately explain the fine-tuning of the universe. And so it appears we're left with one option, namely design. As the astronomer Fred Hoyle writes, a common sense interpretation of the facts suggests that a super intellect has monkeyed with the physics. And so the design hypothesis is that the universe's constants and quantities have the precise values that they do because of intentional design. And so we have observed our first feature of the universe that appears to be design, or that hints to the fact that the universe is designed. So now we'll look at the second feature of the universe that appears to be design. Now, this is with respect to the applicability of mathematics. The fact that mathematics applies to the physical world. And we'll get into what that means and why that suggests design. So first, let's think about the nature of mathematical inquiry. Let's talk about the discipline of mathematics. Now, mathematics is one of those disciplines that is notoriously hard to define. It rejects, rigid definitions because it's just so broad and expansive. But some basic, features of the study of mathematics, of the field of mathematics, is that it's an abstract study of quantities and structures. So it's based in rational investigation, not experience, and it's very broad. That's basically the gist of what we can say, in terms of mathematics. There isn't really a consensus definition of the field, but we can break down some of those components a little bit. So mathematical inquiry is a priori. That's a fancy philosophical term that basically means prior to experience, prior to experimentation, prior to observation. So you can do all of the mathematics that your heart and mind desire without ever looking at the physical world, without ever experimenting on anything or observing anything in the universe or nature. You don't need to do that. You could do the entire thing in your head, or on a whiteboard as an extension of the thoughts in your head. You don't need any experimentation or observation. So it's an a priori discipline. It's prior to any experience. Also, mathematical objects are abstract. So if you remember from the argument from contingency, we focused purely on concrete objects, and now we're talking about abstract objects. But to refresh your memory, concrete objects are objects that are causally endowed. They're endowed with causal power. So for example, I'm a concrete object because I can pick up a laptop and then throw it against a wall. That laptop is also a concrete object because it can force a dent in the wall, So anything that can cause or affect change is going to be a concrete object. Anything that's capable of doing that in principle. Abstract objects, on the other hand, are objects that are not endowed with causal power. They are causally inert. For example, propositions. The proposition, I am standing up giving a lecture right now, cannot cause anything. The proposition itself cannot cause anything. It's causally effete. Now, numbers are the paradigmatic example of abstract objects. The number 7, for instance, can't cause anything. So it's abstract. So far, math is an a priori inquiry into abstract objects. That's at least part of the definition of mathematics, but those are some key components of it. They're necessary elements, if not sufficient ones. If that doesn't give you a complete definition of mathematics, they're at least required ingredients of any good definition. Now, what's important to note is that Math is often developed for internal beauty. Math often arises out of the aesthetical impulse of human beings. And so many mathematicians, from Gauss to Riemann to Hardy, have stressed that mathematics is pursued like art. And so key aesthetic values of mathematics include beauty, right? So elegant proofs, symmetry, simplicity, depth, so the revelation of surprising connections between different branches of mathematics, right? Unity, so subsuming disparate results into a single framework. Fruitfulness, so generating new questions and structures, seemingly just guided by creativity in a lot of ways. And so justification in math often comes from mathematical fruitfulness and coherence, not utility or applicability with the physical world. So math seems to be largely internal. As Wigner himself writes, the great mathematician fully, almost ruthlessly exploits the domain of permissible reasoning and skirts the impermissible. So let's now talk about mathematics' role in physics. So the great Nobel Prize-winning physicist Eugene Wigner in the 1960s published a paper that stunned the scientific community, entitled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So Wigner sees that mathematics, this realm of objects, this field of study that's developed for internal beauty and coherence, this abstract study, this a priori study of abstract objects, applies to the universe. And it applies in two fundamental ways. First, it's useful in physics for evaluating the consequences of the laws of nature. But more importantly, it plays the role of enabling the formulation of the laws of nature themselves in the language of mathematics. So our laws of nature, right, our laws that govern the regularities of the universe, are expressed as mathematical equations, which is very, very interesting. Mathematics seems to apply to the universe in a very fundamental way. So what are some examples of the applicability of mathematics? We'll look into some basic ones before we look at a more complicated one. So Pythagoras noted that if you shorten a vibration string by half, it plays the same note one octave higher. The mathematician Peter Higgs used mathematical equations to predict the existence of a particle that would come to be known as the Higgs boson. Now, after billions of dollars of research and thousands of man-hours, they actually discovered, via experimentation and observation, the existence of the Higgs boson. But yet he predicted it decades beforehand by just using mathematical equations. The existence of Neptune was actually predicted by mathematical equations long before we were able to observe it and identify it with a telescope. So why is that, right? And then even Newton's laws of planetary motion, right? They're expressed mathematically. They're expressed as equations, and those equations chart and predict and explain the motion of planets to a breathtakingly precise degree. And of course, those equations are then refined and perfected even more by more advanced mathematical equations. So those are some relatively simple examples. But now let's look at a more complicated one. Let's look at complex numbers in quantum physics. So complex numbers were developed centuries before modern physics. They originated from attempts to solve cubic and quadratic equations in the 1500s. So they're defined as numbers of the form a plus bi, where I equals the square root of -1, right? We all remember that from high school math, right? Imaginary numbers. And so for a long time, they're considered imaginary and purely formal. And they were prized by mathematicians for internal coherence and elegance, not for their physical relevance. But then, when quantum mechanics, right, is discovered and our equations that discover the world become more advanced and our understanding of the fundamental structures of the universe becomes more sophisticated in the last century especially, complex numbers were found to be essential in, for example, Schrodinger's wave equation. The equation doesn't work if you remove the complex structure. Real valued wave functions can't account for the interference patterns or probability currents we observe. The I encodes oscillation and phase, which is crucial for the quantum superposition principle. Now, even if you don't understand, right, the science behind that, you still get the idea of how useful this is and why it's surprising. Because complex numbers, once dismissed as unreal, became indispensable to describing real phenomena. Think about how striking this is. Math developed for internal beauty and coherence. This idea that you should be able to square every number, not just positive numbers, leads to this development of this thing that's for beauty, right, in this completion in mathematics. And yet, it becomes indispensable in physics. That's surprising. We would never expect that. And we never expect such a close connection in general, that mathematics should be so incredibly useful in describing the fundamental forces of nature. And Wigner himself recognizes the surprise of this. That's the whole point of the paper. He writes, "The mathematical formulation of the physicist's often crude experience leads to an uncanny number of cases to an amazingly accurate description of a large class of phenomena." Now, some people will seek to object to the idea that the effectiveness of mathematics in the natural sciences is surprising in a number of different ways. So first, some people will point to the infinitude of mathematics. So they'll say, well, the realm of mathematics is infinite and the universe is finite. So of course that, right, like given an infinite array of different objects and concepts, that some of them would apply to the physical world. That doesn't seem to be surprising. That seems expected, if anything. The problem with this objection is that it's asking the wrong question. We're not asking why any mathematics applies to the universe. Quite the opposite. We're asking why the universe has a structure that's so amenable to mathematics. Why is the universe even describable in mathematical terms? So the question is on the part of the universe, not on the part of the math. Why does the universe exhibit such a mathematical structure, and such a breathtakingly elegant one as well? So that objection misses the mark. Some people will say that the universe just happens to have a mathematical structure, and that the universe is a mathematical object. So of course it's not surprising that math applies, because the universe is in some sense identical to math. It is just another mathematical object. The problem with this is that Wigner gives several examples of his paper. In his paper, he seems to anticipate this objection of mathematical objects that cannot be physically realized. He gives the examples of imaginary numbers and infinite dimensional spaces. These are things that cannot be physically realized, whereas, for example, 2 might be, right, with 1 chair and 1 chair equaling 2 chairs. You couldn't get something like that with infinite dimensional spaces or imaginary numbers. They cannot be physically instantiated. And so it doesn't seem that the physical world of the universe is going to be isomorphous to mathematical objects, because there's some math that just cannot be instantiated in it. So it doesn't seem like it's going to be identical to math. The next objection, which is posited by atheist philosophers like Graham Oppy, is that the explanation of the applicability of mathematics to the physical world is not going to be, right, a designer. It's just that it's necessary. So these people will agree that, right, mathematics does apply, but they might argue against the fact that it's surprising, or they might say, okay, the explanation to account for that applicability is necessity. So it applies, right? What's the explanation for why mathematics applies to the physical world? Because it has to. It's necessary that it does. So, for example, they might say the universe necessarily has a mathematical structure. And so if you ask them why, what's the explanation? They'll say the explanation is that it's necessary. That's it. That's the end of the story. The problem is necessary facts can still have explanations. I want to ask, why is it the case that the applicability of mathematics to the physical world is necessary? Why does mathematics necessarily apply to the physical world? Right? This move by many atheist philosophers to say that necessary facts can't have explanations seems dead wrong. We can think of a number of examples where necessary facts do have explanations, right? And why that necessity is itself explained. So, for example, it is a fact that I am not a married bachelor. And that's a necessary fact too. That could not be otherwise. But it seems that you can explain that. Why? By the meaning of the terms married and bachelor. Bachelor meaning unmarried. So, of course, I can't be married and unmarried at the same time. So that's a necessary fact, and that's explained by, for example, the definitions of those words and the laws of logic. For example, the law of non-contradiction, which says that something cannot be both A and not A at the same time, in the same way, and in the same respect. So it seems that they can have explanations. Also, 2 + 2 = 4. That's a fact. That's widely regarded to be a necessary fact. And yet there's an explanation of that, of why 2 + 2 = 4. Because the Peano axioms of set theory are necessarily true, because of basic arithmetic. So it does seem that necessary facts can and often do have explanations. So the atheist it's not enough to just claim that the universe necessarily has a mathematical structure or that math necessarily applies. You need to explain why that is the case. You need to explain the necessity. And there's been no attempt given for that. And that seems like a very implausible suggestion that mathematics needed to apply to the physical world. It's very conceivable, right, to imagine a world where mathematics did not apply to it, right? And even just think, mathematical objects, even if they exist, which is debated, if all the numbers were to just disappear, the world around us would not change at all. It would not be affected. So to say that it necessarily operates on a mathematical model, that it needed to operate this way, is just unbelievable, right? There's no reason to expect that. And certainly you can conceive of a universe that isn't describable by complex and beautiful mathematics. So this objection, too, is going to miss the mark. And the interesting thing is that you have some philosophers, like Graham Appy, who say that the applicability of mathematics to the physical world is necessary. And you have other philosophers, like Mary Lang at the University of Liverpool, who argue that the applicability of mathematics to the physical world is a, quote, happy coincidence. So you have polar opposite response to this argument from the atheist philosophers who've studied it. The last objection we'll cover stems from the origin of mathematics. So the objector here will claim that the applicability is not surprising because mathematics was developed to represent physical phenomena. And so it's not surprising that, math applies to the world because a lot of math was developed to describe the world. So it's not surprising at all. But that's not true of all of mathematics. As Wigner himself writes in his famous paper, whereas it is unquestionably true that the concepts of elementary mathematics, and particularly elementary geometry, were formulated to describe entities which are directly suggested by the actual world, the same does not seem to be true of the more advanced concepts, in particular the concepts which play such an important role in physics. Thus, the rules for operations with pairs of numbers are obviously designed to give the same result as the operations with fractions, which we first learned without reference to pairs of numbers. The rules for the operations with sequences, that is, with irrational numbers, still belong to the category of rules which were determined so as to reproduce rules for the operations with quantities which were already known to us. Most more advanced mathematical concepts, such as complex numbers, algebras, linear operators, Borel sets, and this list could be continued almost indefinitely, were so devised that they are apt subjects on which the mathematician can demonstrate his ingenuity and sense of formal beauty. So while certainly some parts of mathematics were developed to help represent the physical world, that's not the case with a lot of others, which arose out of the aesthetic impulse, out of that desire to pursue beauty right, on the part of the mathematician. And a lot of that is the stuff that's actually most useful in physics. And so, a faithful representation of Wigner's argument of the unreasonable effectiveness of math, right, in the natural sciences, combined with a theistic explanation of that, would be as follows. Mathematical concepts arise from the aesthetic impulse in humans and have no causal connection to the physical world. Premise 2. It would be surprising to find that whatever arises from the aesthetic impulse in humans and has no causal connection to the physical world should be significantly effective in physics. Therefore, it would be surprising to find that mathematical concepts should be significantly effective in physics. 3. The laws of nature can be formulated as mathematical descriptions, concepts, which are often significantly effective in physics. 4. Therefore, it is surprising that the laws of nature can be formulated as mathematical descriptions that are often significantly effective in physics. Therefore, the fact that the laws of nature can be formulated as mathematical descriptions that are often significantly effective in physics merits explanation. Now, Wigner was ultimately not a theist, and it seems in this paper that he never took the theistic hypothesis very seriously. And so, what he does is he examines all of the naturalistic or atheistic explanations of the applicability and finds them all unsatisfying, and so therefore says that the applicability of mathematics is a miracle. It's something that we neither deserve nor understand. But what if we take the hypothesis of theism seriously? The hypothesis that there is a designer of the universe. Well, it seems that theism provides a better explanation of the fact that the laws of nature can be formulated as mathematical descriptions that are often significantly effective in physics than does atheism. Therefore, the fact that the laws of nature can be formulated as mathematical descriptions that are often significantly effective in physics provides evidence for theism. Namely, it appears to be an instance of design. And the explanation here would be that a mind-like designer of the universe would have fashioned the physical world on a mathematical model that he already had in mind. And so the reason that the abstract and the concrete meet, especially in such ineffective and such beautiful and elegant and powerful ways, is because the same person who designed the universe built it on a mathematical model. And so you have a perfect bridge of the two, grounded by a wonderful and powerful intelligence that put them together. And so this really appears to be a second feature of design, and therefore another feature that cries out for design. And so we can ask, what is the best explanation for those two facts, right? For those two instances of design? Well, there's one explanation that accounts for both of them. That's simple and elegant and is very explanatorily powerful. And that's that there's a designer of the universe. And so, let's look at the argument once more. If the universe exhibits features that are best explained by design, then there is a transcendent designer of the universe. The universe, with its initial cosmic constants and quantities, fine-tuned for the possibility of the existence of intelligent life, and its elegant mathematical applicability, exhibits features that are best explained by design. Therefore, there is a transcendent designer of the universe. And so, that's the argument for design. So we've now seen that God is the best explanation for why anything exists at all rather than nothing, for the objective moral values and duties that we all experience, and the apparent design of the universe. And so we've seen three powerful reasons to think that it is more probably true that God exists than that he doesn't exist. And so next week, we'll examine the case against his existence. And on balance, at the end, we'll see how the arguments in favor of theism are much stronger, both quantitatively and qualitatively, for the existence of God than the arguments against it. So thank you very much, and we'll see you next week.